Okay, this is part 3 of the first section, extending the particle in uniform circular motion. You are a civil engineer who has been given the assignment to design a curved roadway in such a way that a car will not have to rely on friction to round the curve without skidding. In other words, a car moving at the designated speed can negotiate the curve even when the road is covered with ice. Such a road is usually banked, which means that the roadway is tilted toward the inside of the curve. Suppose the designated speed for the road is 13.4 meters per second. That's about 30 miles per hour. And the radius of the curve is 35 meters. You need to determine the angle at which the roadway on the curve should be banked. So to conceptualize, let's look at the difference between this example and the previous example, is that the car is no longer moving on a flat roadway. The figure shows the banked roadway with the center of the circular path of the car far to the left of the figure. Notice that the horizontal component of the normal force participates in causing the car's centripetal acceleration. Note in the figure that unlike the motion on an inclined plane in the figure, we use a coordinate system with x horizontal and y upward. This choice is made so that the centripetal acceleration of the car is purely in the x direction. So let's categorize this as follows. The car is modeled as a particle in equilibrium in the vertical direction and a particle in uniform circular motion in the horizontal direction. Okay. To analyze this, on a level, unbanked road, the force that causes the centripetal acceleration is the force of static friction between the tires in the road. If the road is banked at an angle theta, however, the normal force N has a horizontal component toward the center of the curve. Because the road is to be designed so that the force of static friction is 0, the component Nx equals N sine theta is the only force that causes the centripetal acceleration. So let's write Newton's second law for the car in the radial direction, which is the minus x direction. Okay, the sum of the forces in the radial direction equals N sine theta equals m times centripetal acceleration, with the centripetal acceleration being v squared over r. It's equal to mv squared r. Okay, now apply the particle in the equilibrium model to the car in the vertical direction. Now, some of the forces in the y is n cosine theta, that's the normal, minus mg, and that has to equal 0. So that's n cosine theta equals mg. Divide the first by the second, and you end up with tangent theta equals v squared equal rg. The m's cancel. The mv squared over r divided by mg, the m's cancel, and you end up with v squared divided by rg. Okay, let's see. Solve for the angle theta and substitute numerical values. So theta is equal to the tangent inverse v squared divided by rg. So you work that out, you get 27.6 degrees. We see that the banking angle is independent of the mass of the vehicle, negotiating the curve. If a car rounds the curve at a speed less than 13.4 meters per second, the centripetal acceleration decreases. Therefore, the normal force, which is unchanged, is sufficient to cause 2 accelerations: the lower centripetal acceleration and an acceleration of the car down the inclined roadway. Consequently, an additional friction force parallel to the roadway and upward is needed to keep the car from sliding down the bank to the left in the figure. Similarly, a driver attempting to negotiate the curve at a speed greater than 13.4 meters per second has to depend on friction to keep from sliding up the bank to the right of the figure. Okay. Imagine the same roadway were built on Mars in the future to connect different colony centers. Could it be traveled at the same speed? No, V would be reduced. The reduced gravitational force, which is 3.711 meters per second squared, on Mars would mean that the car is not pressed as tightly to the roadway. The reduced normal force results in a smaller component of the normal force toward the center of the circle. This smaller component would not be sufficient to provide the centripetal acceleration associated with the original speed. The centripetal acceleration must be reduced, which can be done by reducing the speed v. Mathematically, notice that if we solve our equation for v, tangent theta equals v squared divided by rg, we solve for v, we see that the speed v is proportional to the square root of g for a roadway of fixed radius r, banked at a fixed angle theta. Therefore, if g is smaller, as it is on Mars, the speed v with which the roadway can be safely traveled is also smaller. All right, let's look at another problem. A child of mass m rides a Ferris wheel as shown in the figure. The child moves in a vertical circle of radius 10 meters at a constant speed of 3 meters per second. Part A, determine the force exerted by the seat on the child at the bottom of the ride. Express your answer in terms of the weight of the child, mg. Now, let's conceptualize this. First, we look carefully at the figure. Based on experiences you may have had on a Ferris wheel or driving over small hills on a roadway, you would expect to feel lighter at the top of the path. Similarly, you would expect to feel heavier at the bottom of the path. At the bottom of the path and the top, the normal and gravitational forces on the child act in opposite directions. The vector sum of these two forces gives a force of constant magnitude that keeps the child moving in a circular path at a constant speed. To yield net force vectors with the same magnitude, the normal force at the bottom must be greater than at the top. Let's categorize this as follows. Because the speed of the child is constant, we can categorize this problem as one involving a particle in uniform circular motion, complicated by the gravitational force acting at all times on the child. All right, let's analyze it. We draw a diagram of forces acting on the child at the bottom of the ride as shown in the figure. The only forces acting on him are the downward gravitational force Fg, which is equal to mg, and the upward force at the bottom, the normal force at the bottom exerted by the seat. The centripetal acceleration of the child at this point is upward, and the net upward force on the child has a magnitude of n normal at the bottom minus mg. Using the particle in uniform circular motion model, apply Newton's second law to the child in the radial direction when he is at the bottom of the ride. There we go. The sum of the forces equal to the normal force at the bottom minus mg, and that's equal to the mass times the centripetal acceleration, which is mass times v squared r. Okay, solve for the force exerted by the seat on the child, the n bottom. We solve for that. N bottom equals, we just add mg to both sides. We get mg plus mv squared r. We can, they do a little trick here where they add a g to the denominator of the v squared r, and so you end up with an mg times v squared divided by rg. Then you can use the distributive property to take out the mg. So mg equals to 1 plus v squared over rg. You substitute the numerical values for the speed and radius, and you get 3 meters per second squared, 3 meters per second squared divided by 10 meter radius and g of 9.8 meters per second. That ends up 0.09, and you add the 1, it's 1.09 mg. So with that 1.09, the magnitude of the force and bottom exerted by the seat on the child is greater than the weight of the child by a factor of 1.09. So the child experiences an apparent weight that is greater than his true weight by a factor of 1.09. Now, let's determine the force exerted by the seat on the child at the top of the ride. The diagram of forces acting on the child at the top of the ride is shown in the figure. The centripetal acceleration of the child at this point is downward, and the net downward force has a magnitude of mg minus n top. Sorry about the dogs. So we apply Newton's second law to the child at this position. Sum of the forces is equal to mg minus n top equals to mass times acceleration. Solve for the force exerted by the seat on the child. N top equals mg minus m v squared r. And we do the same trick with adding a g to the denominator of the v squared over r. You end up with mg times 1 minus v squared rg. Okay, let's substitute numerical values, and you see that it's 1 minus the result, and so we end up, in this case, the magnitude of the force exerted by the seat on the child is less than its true weight by a factor of 0.908, and the child feels lighter. The variations in the normal force are consistent with our predictions in the conceptualized step of the problem. Okay, suppose a defect in the Ferris wheel mechanism causes the speed of the child to increase to 10 meters a second, 10 meters per second. What does the child experience at the top of the ride? Okay, in the calculation, if the calculation is performed with v equal to 10 meters per second, the magnitude of the normal force at the top of the ride is negative, which is impossible. We interpret it to mean that the required downward centripetal acceleration of the child is larger than that due to gravity. As a result, the child will lose contact with the seat and will only stay in his circular path if there is a safety bar or a seat belt that provides a downward force on him to keep him in his seat. The child loses contact with the seat. At the bottom of the ride, the normal force is 2.02 mg, and which is basically it's 2 G's, which would be uncomfortable. 2 G's is quite a bit. So this ends our discussion of section 6.1. Next, we'll discuss section 6.2, non-uniform circular motion.